So let's now add some extra detail to our source. We have our sphere. Be sure that this is set to polygon. We have 3 on the frequency. Let's use a attribute noise, or better yet, a random attribute or attribute randomize. The names get kind of crazy sometimes. Let's set this to scale, 3 dimensions, X, Y, and Z. The minimum is going to be a scale of 0.25, like that. The maximum is going to be 1. That gives us these non-perfectly spherical shapes, like that. And if we combine this with another attribute randomized for the p-scale, that controls the overall scale, right here, dimensions 1, we end up with something like this. Now, one thing that we could also try to do is use the relative bounding box to scale up any sort of points down towards the bottom and leave them smaller towards the top. So if we want to do that, we already have this height attribute that we can use. So what if we create a point wrangle, and all we said as an example was f p-scale times equals at height. What would that do? Something like this, which is too small, but then we can multiply this by something else. So we could say channel float, and we could say p-scale underscore molt. And now we have a slider to adjust all the p-scale components like so. So now we can end up with something like that. Now, I do want to remap this height though, so we can make a channel ramp of that. Call this our p-scale control. And that will allow us to better determine what we want for the distribution. So if we want to go up on that, which we do, we could do something right around here and then get more of a minimum going. Take that in combination with the p-scale molts, and that's going to be looking a lot better. So something maybe right around there. From here, it makes sense to use the mountain sop to break up these shapes even more, but be careful because we still have this height attribute happening right here. So we'll create a attribute delete, and we'll delete height, and then we'll use a mountain sop. I've gone ahead and skipped forward in the video because by now you guys should know how to use a mountain sop, and I don't want to take your time on that. So these 2 mountain sops are happening. It's a combination of an alligator noise and a purlin noise. And then we take this to VDB from polygons. Instead of calling this density as a fog VDB, let's rename that to fuel. We're still going to be testing this with the Axiom solver, so for that reason, it makes sense to make fuel and temperature. But before we do that, let's also create a volume visualization. Set this to fuel, density scale up, shadow scale up, turn on our lighting right here. Also, set the VDB from polygons to 0.05. And we also want to add a bit of noise to this volume. So let's create a volume VOP. We'll bind fuel. So there's a bind. We need a bind export as well. Both of these guys will be using fuel. Plug them in. Let's create a anti-alias noise. And with the anti-alias noise, this has a value between -0.5 and +0.5. So we need to fit that using a fit sop. -0.5, +0.5 from 0 to 1, or 2, 0, and 1. Let's multiply that against our original noise, like so. Also set a ramp, so a ramp parameter after that fits, and promote all the parameters on the AA noise. This is just basic Houdini stuff, really, at this point. So, plugging this in over here, let's go ahead and bring forward our ramp like so. Also, let's create a volume slice because that's easier to see what this is doing. All right, with that volume VOP, let's go ahead and turn up the frequency to maybe a smaller value of around 3. Turn up the roughness like that, amplitude of 1, and I like having a bit of contrast up here like so. Okay, great. That adds a bit more detail to this source, and you might not be able to see it very well in the viewports, but that makes a difference when it goes to simulate for sure. Let's also make temperature out of this, so we can literally just copy this whole thing, and let's go ahead and just create a different seed to this, like so. Use a primitive wrangle to rename this now to temperature. So at name equals temperature. And then we can just merge these two guys together. So that gives us fuel and temperature. And both of these are around 300,000 voxels. Again, you could go up a little bit from here if you want, but try to keep it around 300 to 500,000. Okay, awesome. Well, that pretty much does it for our sourcing for fuel and temperature. Now, you might be thinking, wow, that took a long time to just make that source. And if I was in production, I wouldn't really have the time to do that. And compare that to what I get with the Pyro Burst source, which is like right away. Well, here's the deal. Now that you've built out this whole thing, all you need to do is make a subnet and turn that into an HDA, and it pretty much works with anything you plug into it from now on out. So it'll take you time to build this at first, but do remember that all we need to do now is just copy these nodes, paste it into a subnet, which is this guy down here, and it'll pretty much work instantaneously for the other sources that you have. So let's plug that in, bring our outputs all the way down here. And if we plug in this guy, we get a source. It'll take a second to think about it, but boom, there we go. And that's all in the shape of what we see from our render cam. So from now on, you can take everything we just did and make this into a Sourceify subnet, where you basically just either draw a curve in your viewports, or you can do what we did and use the trace SOP to bring in an image, and with that image, it'll become the source that you're trying to get. So this is a fantastic tool to use in the future if you're trying to source anything. Yes, you can go ahead and make this better by having user parameters and making more user-friendly adjustments to this whole system. But the fact of the matter is, you now have the ability to just draw something in your viewport and get a source from that silhouette, which is amazing. So that, I think, does better for this situation than the Pyro Burst source. And once you have it, it's even faster than this guy, potentially. So that's really cool. In the next video, let's blend these two sources together, cache it out to disk, and then see what happens when we plug that into the Axiom solver.